Hi guys, we're continuing to talk about Chapter 6, Periodic Trends, and we are going to talk about two properties today and their trends on the periodic table. So the two properties we're going to talk about are atomic radius or atomic size. Obviously, if the radius of the atom is bigger, then the size would be bigger. So we kind of use those interchangeably because they kind of correlate together. And then the other property we're going to talk about is effective nuclear charge or effective nuclear force. So let's start by defining what those mean. We're going to start with atomic radius. So atomic radius is what it means. It's the radius of the atom. And if you remember from the quantum mechanical model, the nucleus is super small, and then the rest of the atom is basically empty space with these tiny electrons floating around. So it's pretty easy to detect where the nucleus is. It's kind of hard to detect where the end of that electron cloud is. And so what they do is they pick two neighboring nuclei, and they look at the distance between them. They measure that, and they say, well, half of that distance is the radius of one of the atoms. So let's write that down. It is half the distance between the nuclei of two neighboring atoms. Let's think about the units that we would use. So since this is a distance, so we'd use units for distance. So we can use meters. But these atoms are really tiny, so a lot of times we use nanometers or picometers or angstroms or something like that. Okay, our other property that we're going to be talking about is effective nuclear charge. So let's first start with nuclear charge. So if you remember when we started talking about subatomic particles and atomic number and all that stuff, Z represented our atomic number. So Z is our atomic number, which also represents the number of protons. Z, or the atomic number, is also known as the nuclear charge. Now, why would we call it that? Because it's the charge of the nucleus. If you remember, the nucleus has protons and neutrons are neutral, protons are positive, of course. So the charge of the nucleus would be how many protons there are, because those are the charged particles that are in the nucleus. When you see Z with a little EFF as a subscript like this, that is effective nuclear charge. Let's write that down. Effective nuclear charge. And what does that mean? Well, effective nuclear charge is the net attraction between the nucleus and the valence electrons. So still, what does that mean? So let's say that we have an atom where the nucleus is here. Remember, nucleus has positive protons, right? There are positives here. And then here's your valence electron. Well, that valence electron experiences two forces. It is attracted to the nucleus. So there's a force of attraction between the nucleus and the valence electrons. The reason is electrons are negative and the protons in the nucleus are positive. So positive and negatives attract each other. But there's also another force, and that force is a force of repulsion to the other electrons, right? Electrons are all negative, and so they repel each other. They cannot stand each other. They want to stay as far away from each other as possible. So that valence electron is attracted to the nucleus, but it's also repelled by the other electrons. And so the net attraction, so when you take into account these two forces together, the net, the resulting is an attraction, but it's a lower attraction. And that resulting attraction is what we call effective nuclear charge. It is, again, the net attraction between the nucleus and the valence electrons, taking into account that repulsion between the other electrons. So size or atomic radius, and this Zeff, this effective nuclear charge, are kind of related to each other. So let's think about, what the trend is in these properties as you go across a period in the periodic table, as you go down a group in the periodic table. So this question here tells you, what trend in atomic radius do you expect to see as you go down a group and across a period in the periodic table, and justify your answer. So I want you to take a few seconds to think about this. What do you think? Would the atomic radius or size increase or decrease as you go across the period and down a group on the periodic table? So pause the video, think about it for a second, and then replay the video again. So hopefully you thought about it. There's not really a wrong or right answer, because this is just what you think right now. As a student, before I learned some chemistry, I thought, well, if the nucleus is super small and the most of the atom is the electron cloud, I thought, well, if there's more electrons, the electron cloud will be bigger, right? So whether I go down or across, if I have more electrons, it's going to get bigger. Turns out I was not really correct, at least not fully correct. So let's look at what really happens to the atomic size or the atomic radius. So these are, this is a data table that shows you the atomic radius in picometers and the different elements here. So maybe it tells you here to build this model with straws. So I built my model with wood, but it's the same thing here. So let me show you. Here are my different elements. And based on that atomic radius that it tells me here, I built this model. And let's see what we notice, what the real trend is. So it looks like, let's start with down a group. So if I look at the first group here, hydrogen to lithium to sodium to potassium, it definitely looks like my atomic radius is increasing as I go down a group. As I go across a period, so if I go from, let's go with the second period, lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine to neon, looks like it's decreasing. So down a group, my atomic radius is increasing. Across a period, it looks like it's decreasing. So let's write down that trend and then think about why the trend is the way it is. So for atomic radius trend down a group, we said it was getting bigger. The radius is increasing. Across a period, we said it's getting smaller. It's decreasing. Now let's think about the attraction, Zeff, right? Remember, Zeff is the net attraction between the nucleus and the valence electrons. And you can think about Zeff, the attraction, causing the size trend, or you can think about the size trend causing the Zeff trend. So let's think about this. Let's go down a group first. So if I go down a group, my atomic radius is increasing, it's getting bigger. So that means my atom is getting larger. What does that mean in terms of attraction? If it's farther away, what does that mean? That means that there's not as much attraction, right? If you have two magnets and they're really close to each other, there's going to be a strong attraction. If you have the same two magnets, but you hold each one at the end of the two ends of a room, they're so far apart, they're not really going to attract, right? So the farther you are, the less the attraction. So looking here for the trend, let me make my picture a little smaller here. So the Zeff trend, as you go down a group, because the size is getting so much bigger, there's not as much attraction. The attraction is decreasing down a group. And as I go across, I can see that my atomic size or radius is getting smaller, which means the valence electrons are closer to the nucleus which means there's stronger attraction. So that increases. Right? So we're saying that the size is causing an effect on the attraction. Well, you can think about it also the opposite way. So you can say that the attraction is causing the size trend. So you can say, as you go down a group, we said that the Zeff, the attraction, is less. Well, if you have less attraction, then it's not going to hold the electrons very close. And so the size will increase if there's not as much attraction. As you go across a period, we're seeing that attraction increase. And so if there's a lot of attraction, the nucleus is going to pull those electrons close to it. And so the radius will get smaller. So again, you can think of Zeff causing the trend in the size, or the size causing the trend in Zeff, but you can tell that they are definitely related to each other. So let's talk about why we're seeing these trends. So let's look at a periodic table. And hopefully you can see the periodic table behind me here. So whether you go down a group or across a period, two things are happening. In both instances, so as you go down a group from like lithium to sodium to potassium, or as you go across a period, so from lithium to beryllium to boron, in both cases, you're increasing the number of protons, right? Your atomic number increases and you have more protons, which would make you think, oh, there's stronger attraction then, there's more positives, and so it's going to attract the more negatives, right? If you think about it, if you have just two little magnets, they will attract each other. But if you have 10 magnets, the attraction is going to be stronger. So the more positives, the more protons, and the more electrons, the more the attraction, right? So both ways, whether you go down or across, you're adding more protons. Okay, well, that causes more attraction. Well, but also, if you go down or if you go across, you're also adding more electrons. And electrons repel other electrons, and so there's also more repulsion. So both ways, it seems like there's a reason to make it more attracted because of the protons. There's also a reason to make it more repelling because of the electrons, which would cause the net attraction to be less. Right, so which one wins? It seems like one is winning one way and the other is winning the other way. So it all has to do with where these extra electrons are being added. So let's look at down a group first. If you go down a group, so you go from lithium to sodium to potassium and so on, yes, you are adding more protons, more positives and negatives, but you're also adding those electrons. And where are these electrons being added? They are added to new energy levels, right? If you think about it, the valence electrons in hydrogen are in the 1s. Valence electrons in lithium are in the 2s. These are in the 3s, 4s. So they are in a whole new energy level. Here is a visual. Hopefully you can see this on your screen. Looks like you can see sodium, potassium, rubidium, cesium. So down a group, the nucleus would be where the line is here, and then the valence electrons are here. So look at these valence electrons versus these valence electrons versus these valence electrons. What's happening? Well, they're getting farther and farther and farther away, right? Why? Because these extra electrons are being added to new energy levels, and so they are being blocked by the other electrons. So I'm going to draw this here. So this is, let's go with lithium. So these are the electrons that are in the first energy level. And then here is my valence electron in lithium. Okay, now let's look at sodium. So here's my nucleus. Here are my 2 electrons in the first energy level. I have 8 electrons here. I don't know how many I drew. 1, 2, 3, 4, 5, 6, 7, 8. That's the second energy level. Third energy level, here's my valence electron. So there is a force of attraction between the valence electrons and the nucleus because protons, electrons attract. Same thing here. Nucleus, positive protons, valence electrons are negative, they attract. So there's a force of attraction between these, right? But there's also a force of repulsion by those electrons that are in the middle. They're kind of in the way, right? So there's a force of repulsion here. And so if you look at lithium versus sodium, oh, there's a bunch of electrons here and a bunch of electrons there. These extra electrons that are in other energy levels are blocking those valence electrons from getting the attraction to the nucleus. And so we call that shielding. The core electrons, the electrons are in the middle, are shielding the valence electrons from the attraction of the nucleus. And so as you go down the group again, your valence electrons are in higher and higher and higher energy levels. And so those core electrons that are in the middle are blocking it, are causing a lot of repulsion and shielding those valence electrons from the nucleus. And so the net attraction is actually less. Because there's not as much attraction as you go down a group between the nucleus and the valence electrons, that attraction gets less and less and less. So the size gets bigger and bigger and bigger because there's not as much attraction. So the electrons are just held looser. The nucleus is not really pulling them close to it. And so the size gets bigger. Okay, let's look at across a period. So what happens across a period? So across a period, I am adding more protons again. So we think more attraction, right? But then you say, well, we're also adding more electrons. But where are those electrons being added? That's the key. So as you go across, your extra electrons are being added to the same energy level. If they're added in the same energy level, they're not really blocking the valence electron from getting to the attraction of the nucleus. And so there's not as much shielding, there's not as much repulsion if they're just next to each other versus blocking each other. And so what wins here is that I have more protons. So let's look at this here. Hopefully you can see it better with this. So this is going across a across a period, I apologize, across a period. So boron to carbon to nitrogen to oxygen to fluorine. The nucleus is right here, right? The bottom here. These are the 1s, the 2s, 2p. So you can see that here in my 2p I have 2 electrons. Here I have 4 electrons. Here I have 5, 6, 7, right? So I am adding more electrons. But where are these electrons being added? They're being added right next to each other there in the same energy level. And so they're not really blocking anymore. The attraction between the nucleus and these valence electrons is about the same for all of them in terms of not having repulsive forces, right? So you would think it should be the same, but actually it's more because there are more protons as well. So your extra electrons are not really doing much because they're in the same energy level. You do have extra protons in the nucleus, more positives to attract those electrons. And so as you go across a period, your attraction, your Zeff, your net attraction between the nucleus and the electrons gets stronger and stronger and stronger. And so that nucleus pulls the electrons towards it more and more and more. And so your size gets smaller and smaller and smaller because the attraction is increasing. So again, let's summarize what we just talked about. As you go across a period and down a group, both instances, you are adding more protons, more positives to attract, but you're also adding more electrons to repel. Which one wins? As you go down, the electrons win, the repulsion wins, because those electrons are being added to additional energy levels, so they're in between, so the repulsion is very, very strong. So the net attraction is less, and so because there's not much attraction, the atom gets bigger. As you go across, again, you have more protons to attract, more electrons to repel, but where are these electrons added? They are added to the same energy level. And so when they're added to the same energy level, the attraction wins. The fact that there's more protons wins, because those extra electrons are not really doing much more to the repulsion, but those extra protons are attracting more. So the net attraction as you go across increases and increases and increases because it's stronger attraction, it's pulling the electrons towards it more, and the size of the atom gets small. So let's try to write this down. Let me minimize my picture here. And let's write the reasoning for what's happening here. So I'm going to start with the Zeff trend, and then I'm going to go to the size trend. So this is down a group, if you remember, and this is across a period. So as you go down a group, the main thing to remember when you're coming up with these reasons is where are your extra electrons being added. So my extra electrons as I go down are being added to new energy levels, additional energy levels. So as you go down a group, the valence electrons are added to additional energy levels. I'm going to use N as a shortcut for my energy levels. Okay, so because these extra electrons are being added to new energy levels, they are farther and farther away from the nucleus. So the valence electrons are farther from the nucleus. And because they are farther away from the nucleus, then there's not as much attraction between the nucleus and those valence electrons. So Zeff, which is the net attraction between the nucleus and the valence electrons, decreases. So you don't have as much attraction because the electrons are too far away. Okay, let's look at, I'm going to change my color here. Let's look at as you go across. So as you go across, again, the first thing you think about is where are your extra electrons being added. So the valence electrons here are added to the same energy level. So that tells me the repulsion is not much different. However, I also have more protons being added in the nucleus. More protons in the nucleus. So since my repulsion is about the same, but I do have more protons, my net attraction is stronger and my valence electrons are closer. Valence electrons held closer to the nucleus. The Zeff, or the net attraction between the nucleus and the valence electrons increases. I have stronger attraction as I go across. Now let's write the reasons for the atomic size or the atomic radius trend. And you'll see the reasons are basically Zeff. Zeff is going to be your best friend in this chapter. It should be your best friend because it explains all the other trends that we see in all the other properties. So we're going to use Zeff to explain our trend in size. So we're going to say down a group, what's the first thing you think about? Where the electrons are being added. So extra electrons as you go down a group are added to additional energy levels. So valence electrons added to additional energy levels. So what does that mean? That means that they're going to shield the electrons from getting to the nucleus. They're going to repel more. The repulsion is winning here. So Zeff, which is the net attraction between the nucleus and the valence electrons, decreases, less attraction. So what does that mean? The electrons held looser, not as much attraction, so atomic radius increases. Okay, let's look at as you go across the period. So first thing you think about is what happens? Where are your extra electrons being added? So as I go across the period, my extra electrons are being added to the same energy level. So valence electrons added to same energy level. At the same time, I have more protons in the nucleus. So what does that mean? If my electrons are being added to the same energy level, there's not much more repulsion, but at the same time I have more protons, so that means more attraction. So the net is there is more attraction to the nucleus. So my Zeff, which is the net attraction between the nucleus and valence electrons, increases. Stronger attraction, what does that mean? Well, if there's a strong attraction, then the electrons will be held tighter or closer. And so that means your atomic radius decreases. Okay. It is really important to understand, especially the Zeff trend. From the Zeff trend, you can come up with the trend for all the other different properties. So make sure that you understand that. Again, Zeff is going to be your best friend in this chapter. Also, make sure you understand what it means. That's why I keep writing Zeff, and then in parentheses I write the net attraction between the nucleus and the valence electrons. It's repetitive, but it will help you understand what it means. If you just write Zeff, then sometimes that doesn't click in our mind what that really actually means. All right, I hope you guys have a wonderful rest of your day. Bye.